May 1946, inside the engineer school at Fort Belvoir, US officers ushered former Wehrmacht bridge specialists into a lab where Bailey trusses loomed over test jigs. Months earlier, Allied columns had relied on treadway and Bailey spans to cross Europe. Now the Army wanted crossings faster to erect, stronger under tanks and easier to move. American intelligence had swept up German technical troves through CIOS and the Field Information Agency, Technical. In parallel, Operation Paperclip transferred scientists and engineers to US posts for government work, ultimately more than 1,600 personnel. Engineers studying captured pioneer equipment and manuals noted modular floating gear, rapid launch assault spans, and load schemes the Wehrmacht refined under fire. American test reports praised the wartime M2 treadway as a breakthrough, yet field experience revealed limits whenever speed, mud, and heavy armor converged. The question became unavoidable. If Germany's engineer corps had pushed field bridging hard, could US teams, reinforced by captured expertise and documents, leap beyond those limits in peacetime labs and NATO exercises? Army histories record nearly 600,000 engineer troops in World War II and a post-war mandate to turn combat lessons into doctrine, equipment and training at Fort Belvoir. From Fiat reports to post-war proving ground trials, the paper trail shows a clear intent: translate adversary technique into American overmatch. This episode did not begin with friendship. It began with urgency and a calculation that the fastest bridge is the one you can build today with the best ideas you can lawfully take. So how did US engineers fuse German data, American industry, and battlefield lessons into bridges that surprised specialists who once opposed them? According to military records and declassified programs, the answer unfolds in the months after victory, when the engineering war continued on American soil. By 1943, the Wehrmacht's Pioniertruppen, its elite engineer corps, had become the envy of every major army in Europe. German field reports archived at the Bundesarchiv Militärarchiv RH 7103 describe these units as soldiers of science, capable of erecting assault bridges under artillery fire and dismantling them before dawn. During the Rhine defensive operations of March 1945, their modular bridge systems, particularly the Kriegsbrückengerät B and Gerät C, carried 60-ton Tiger, I tanks across rivers that Allied reconnaissance had marked impassable. Captured field manuals, later translated by US technical intelligence teams, reveal meticulous German calculations. Each 10-meter span required 12 men, 22 minutes, and 18 aluminum segments reinforced with manganese alloy. Their bridges could withstand dynamic loads 25% higher than Allied equivalents, an advantage that stunned US engineers at the Aberdeen Proving Ground when they tested captured equipment in late E-1945. The precision is astonishing, noted one American officer in the CIOS report, number GEX 112. They achieved stability with fewer components than any design we possess. This technological superiority fed an almost mythic confidence. German propaganda films in 1944 portrayed pioneers erecting crossings over the Dnieper amid flames, while soldiers joked that no river can halt the Reich. Even in the final months, internal communications recovered from the OKH engineer department. Show officers dismissing Allied bridge building as mechanically crude. Their reports claimed American pontoon systems lacked the rigidity for heavy armor, a statement later disproven by US operational data. Such arrogance blinded the German command to the industrial scale of American problem-solving. Where Germany had mastered precision under scarcity, the United States would soon apply abundance to refinement, turning captured blueprints into mass-produced innovation. Yet in 1944 the balance seemed certain. The Wehrmacht's engineers built faster, lighter and stronger. Allied intelligence rated German pioneer engineering the most advanced in the world, and British Royal Engineers admitted privately that we study their failures. as if they were victories. At the war's end, when Allied forces seized 1,500 tons of German technical archives, they realized just how far behind they had been. What the Germans considered routine would soon become the foundation for an American revolution in military engineering, one born not from imitation, but transformation. In the early 1940s, American military engineering lagged far behind its European rivals. The U.S. Army Corps of Engineers depended primarily on the British-designed Bailey Bridge, an ingenious yet cumbersome structure that required heavy manpower and time-consuming assembly. Official field records from the European Theatre of Operations, ETO Report 44B, describe units struggling to span French rivers under enemy fire, where 1 in every 4 bridge segments failed due to stress fractures or alignment errors. By comparison, the Wehrmacht's modular systems achieved similar spans with half the time and materials. U.S. logistics files from NARA RG 338 document frequent shortages of high-grade alloy steel, forcing engineers to rely on mild steel and limited aluminum stocks reserved for aircraft production. As Colonel George W. Goethals Jr. wrote in a 1944 memo, "We can build a bridge for every tank we have, but not in the time war demands." Even among allies, skepticism was clear. A confidential British Royal Engineers assessment in late 1944 judged American bridging equipment serviceable yet uninspired. Newspapers back home called for demobilization, reducing research budgets, and leaving Fort Belvoir's testing grounds eerily quiet by mid-1945. Yet beneath the surface, an invisible war of innovation began. Intelligence officers from the Combined Intelligence Objectives Subcommittee, CIOS, shipped captured German engineering drawings to Virginia and Maryland under heavy guard. These archives contained data on folding aluminum spans, buoyant pontoons, and load-balancing methods the U.S. had never attempted. A declassified Pentagon directive dated November 1946, Paperclip Annex E, instructed Army technical divisions to retain, recruit or repurpose German personnel of engineering value. The American Corps, short on innovation but rich in industrial might, realized that knowledge, not steel, was the true post-war weapon. Fort Belvoir became the crucible for that transformation. Between 1946 and 1947, a handful of German engineers quietly joined American research teams, analyzing bridge stress curves with slide rules and chalkboards. Their mission was no longer conquest, but correction, to turn battlefield lessons into blueprints for the future. From that unlikely partnership, the underdog began to rise. By late 1946, while most Americans believed the war's engineers had gone home, the U.S. Army Corps of Engineers had quietly transformed Fort Belvoir, Virginia, into the epicenter of a classified reconstruction effort. Under Operation Paperclip, a select cadre of German bridge specialists was assigned temporary civilian status and relocated to assist in post-war testing. According to declassified Pentagon Directive 1946-11, these men were tasked not with building new weapons, but with refining the American bridge itself. Their first challenge was the M2 Treadway Bridge, the Allied workhorse of World War II. Field data from the Army Service Forces Technical Bulletin No. 205, 1945, showed that under heavy load or turbulent currents, its pontoons often failed. When engineers compared the design to captured German Kriegsbrückengerät specifications, they found the enemy's modular segments could carry 15% greater weight while using less material. This revelation stunned Major General Hugh J. Casey, the Army's chief engineer, who ordered the creation of an accelerated improvement cell to incorporate these findings. German engineer Dr. Walter Weber Jr., a structural analyst from Bavaria, later recalled, "They asked us to repair their bridge. We built them a new one." His notes, preserved in the Fort Belvoir archives, R&D Notebook 1947, detail collaborative experiments with American metallurgists testing lightweight, alloys and collapsible float systems based on pneumatic pressure, direct evolutions of German field innovations. In 1948, this secret collaboration produced the M4 floating bridge, capable of supporting 70-ton loads, enough for the M26 Pershing tank. Laboratory reports recorded test spans over the Potomac, achieving record-breaking assembly times, 19 minutes from first anchor to final alignment. For the first time, American bridges outperformed their European counterparts in every measurable metric. This rapid progress did not go unnoticed. Soviet intelligence reports, CIA declassified file, FE-12-7 warned Moscow that the American Army now possesses superior crossing capabilities for mobile armor divisions. Yet, the true success of Fort Belvoir's engineers lay beyond secrecy, the merging of wartime rivalries into cooperative science. By 1950, the U.S. Army Engineering R&D Laboratory had evolved from a repair shop into a think tank. Its engineers were no longer just building bridges. They were reimagining how nations moved, fought, and rebuilt. As General Casey wrote in a 1953 memorandum, "We have surpassed the engineers who once opposed us, not by erasing their work, but by improving it." By 1947, Fort Belvoir's once sleepy proving grounds had become a hive of controlled secrecy. Army engineers, civilian metallurgists, and recently integrated German specialists worked side by side in what official memos called Bridge Test Facility No. 2. The facility's project diaries, now housed in the U.S. Army Corps of Engineers Historical Division, record testing days that began at dawn and stretched deep into the night. Each team logged temperature, humidity, wind speed, and even soil moisture, every variable that could affect bridge performance. Declassified correspondence from Major General Hugh J. Casey, NARA RG-77, File 205A, shows how tightly the schedule was managed. "We must outpace the Soviets in engineering before they outbuild us in steel," he wrote in December 1947. Referring to intelligence that Soviet units were reverse engineering captured German pontoon designs. To safeguard its advantage, the Army imposed strict compartmentalization. Engineers signed new secrecy oaths, and even maintenance crews were rotated weekly to prevent familiarity with the prototypes. Weather nearly derailed the operation. The Army Weather Service logs record that a snowstorm on January 28, 1948, dropped 8 inches over northern Virginia, halting outdoor testing for 3 days. Yet laboratory notes reveal that even during the blizzard, engineers continued assembly trials indoors using scaled models and hydraulic simulators, a testament to their urgency. Meanwhile, the geopolitical climate added tension. A CIA field memorandum, FE-12-7, from the same winter reported that Soviet observers believed American combat engineers lack original technical capacity, that misjudgment would soon cost them dearly. On March 14, 1948, at 09:17 hours, Fort Belvoir logs mark the first full-scale trial of the Rhine-America Prototype 1, a 220-foot modular bridge assembled over the Potomac Test Basin. Eyewitness engineer Harold McInnes wrote, "We broke the stopwatch before the bridge broke the waterline. The span bore 70 tons without structural failure, setting a new world record for rapid military bridging. The stage was now set." America's engineers had moved from imitation to innovation, from secrecy to supremacy. Within a year, these trials would cross the Atlantic for NATO field exercises, where the rest of the world would witness what the German pioneers themselves called Die Brücke der Zukunft, the bridge of the future. In the spring of 1949, the results of 2 years of clandestine testing emerged from secrecy. During exercise Combat Bridge, held near the Weser River in the British occupation zone of Germany, U.S. Army engineers demonstrated the M4 floating bridge, a direct descendant of the Fort Belvoir prototypes. According to the official U.S. Army After-Action Report, June 1949, assembly began at 06:42 hours under cold rain and was completed by 07 Bruce hours 18 minutes flat. The bridge carried an M26 Pershing tank across a 200-foot span without measurable deflection, shattering all previous Allied records. Film from the U.S. Army Signal Corps. Reel 1038 captures the moment. Engineers, American and former, German, working shoulder to shoulder as the final span locked into place. Onlookers from Britain and France applauded openly. "The Americans have outbuilt us all," one British officer murmured, his comment preserved in the reel's contemporaneous transcript. To those present, it was more than a demonstration. It was the symbolic closing of the engineering gap that had separated the Allies from the Wehrmacht. Official evaluations recorded performance gains that stunned observers. Load capacity increased by 22% over the wartime treadway. Assembly manpower had dropped from 40 men to 26. The new pneumatic pontoon system, derived from German Kriegsbrückengerät research but refined through American industrial scaling, allowed rapid inflation and seamless alignment. U.S. technical officers described the result as a mechanical orchestra conducted in minutes. One eyewitness, Sergeant David Rowe, later wrote in his field diary, "The Germans who once built bridges to stop us now build bridges to carry us forward." That single line encapsulated the transformation, taking place not just in technology but in mindset. Soviet military attachés, invited to observe the exercise, were less impressed. A CIA declassified summary, FE 15-49, notes that Soviet observers departed early, citing weather, though subsequent intelligence intercepts revealed alarm. Moscow's engineers had underestimated American field innovation. By evening, when the last tank rumbled ashore, the bridge had withstood 12 full crossings without structural fatigue. The final load test pushed 80 tons, nearly 30% beyond design specifications, and the bridge held firm. Engineers dismantled it in 15 minutes, achieving what wartime manuals had called operationally impossible. The official verdict in Fort Belvoir Technical Bulletin 7-51 summed it plainly. Allied bridging superiority is now unquestioned. From the laboratories of Virginia to the rivers of Germany, American innovation, fortified by captured knowledge and disciplined adaptation, had turned the tide of engineering dominance. This decisive moment was not merely a victory of design, it was a revelation of philosophy. Where the Axis had built for conquest, the Americans built for mobility, for reach, for peace. And in the roaring echo of tank treads over steel decking, history heard the sound of a new era beginning. For the German engineers now wearing U.S. Army-issue workcoats, the spectacle on the Weser River was both triumph and reckoning. Many had once designed bridges meant to halt Allied armor. Now they applauded as Pershing tanks rolled across a structure of their own improved making. In those moments, recalled engineer Otto Renz in his 1948 debrief transcript, NARA RG 389, Box 1142, we understood that our science no longer belonged to a defeated nation. It belonged to the future. Captured communications and post-war interrogation files confirmed genuine astonishment among former Wehrmacht pioneers who had believed American engineering to be crude. Reports from Bundesarchiv BW-1215 document post-war interviews in which several officers admitted surprise at the speed with which the U.S. adapted their concepts. They achieved in 1 year what we required 5 to perfect. One interview reads, "Meanwhile, across occupied Europe, Soviet intelligence networks scrambled to reassess. The East German Intelligence Report T-53, 1950, later declassified, warned Moscow that U.S. combat engineers have exceeded the technical capacity of all previous German models. The same report lamented that many of Germany's best field designers were now working for Fort Belvoir under American contracts, a blow to Soviet ambitions of absorbing German expertise. At Fort Belvoir, the mood mixed pride with disbelief. Test logs from April 1949 record multiple visits from British and French delegations who had come expecting to critique but left requesting copies of the new US design schematics. The once underdog nation had surpassed its mentors. German observers, now collaborators, watched as their wartime doctrines were rewritten into American manuals. The 1950 Engineer Training Pamphlet 5/12 introduced rapid modular deployment, a concept lifted almost word for word from Wehrmacht manuals, but perfected through American industrial scaling. What had begun as post-war pragmatism had become total integration. By the end of that year, the phrase American bridge superiority appeared in NATO briefings, a quiet acknowledgement that the balance of engineering power had shifted decisively westward. For the men who had once built for Hitler's army, the realization was stark. The bridges of their imagination now carried the armies of democracy. The shockwaves from the visa demonstration rippled through every military planning room in Europe. Within weeks, NATO engineers convened at SHAPE headquarters in Fontainebleau to study the US Army's new bridging doctrine. According to the NATO Technical Bulletin No. 2, 1951, American field crossings could now be executed at twice the speed of any known European system, with assembly times under 20 minutes and structural endurance rated to 70 tons. This represented a 30% operational efficiency gain since 1945, a revolution invisible to the public yet decisive. For Cold War logistics, the Army Chief of Engineers' Annual Report, 1952, framed the change in broader terms. Our bridges carry freedom across every frontier. The report credited Fort Belvoir's Research and Development Laboratory for merging wartime innovation with post-war industrial capability. Between 1949 and 1952, the United States manufactured over 4,200 M4 floating bridge kits, enough to span the Rhine 5 times over. The Korean War provided the ultimate proving ground. Field reports from the 8th U.S. Army, 1951, confirmed that treadway sections derived from the Belvoir models allowed armored columns to cross the Han River under combat fire in record time, 19 minutes from assembly to first vehicle passage. Without those bridges, wrote Lieutenant Colonel Thomas M. Johnson in his 1952 memoir, our advance would have frozen before winter did. The Soviet response was swift and defensive. Intelligence cables intercepted in CIA file FE 1952 reveal Moscow ordering the Red Army's Engineer Corps to replicate American modular bridging principles. Yet their prototypes, constrained by material shortages, could not match the American blend of aluminum alloys and pneumatic float technology. Meanwhile, U.S. newspapers like Stars and Stripes, June 1950 edition, celebrated the peace bridges of democracy, portraying engineers as the silent guardians of global stability. What had begun as secret collaboration evolved into open demonstration, a message to allies and adversaries alike that American ingenuity had turned the machinery of war into instruments of reconstruction. By 1952, the United States held undisputed dominance in military bridging, a feat achieved not merely through steel and rivets, but through learning, adaptation, and the will to turn yesterday's enemy into tomorrow's asset. By the mid-1950s, the innovations born in the secrecy of Fort Belvoir had become the cornerstone of modern military engineering. The U.S. Army Engineer Doctrine Review, 1955, officially credited the M4 floating bridge and its derivatives with redefining rapid river-crossing tactics. The report traced a direct line from captured German Kriegsbrückengerät designs to the modular aluminum spans now standard across NATO. It was the ultimate act of technological alchemy, turning enemy science into a weapon for peace. Academic assessments from West Point's Department of Military History, monograph number 14, 1989, later concluded that post-war collaboration between American and German engineers exemplified adaptive warfare in its purest form. The synthesis of German precision and American production capacity produced not just new bridges but an entirely new doctrine emphasizing mobility as deterrence, Between 1950 and 1960, Fort Belvoir graduates exported this doctrine worldwide. U.S. military assistance programs introduced the M4 and its successors to 23 Allied nations. By the 1960s, even civilian infrastructure projects borrowed design cues from these military systems. The same joint lock mechanisms used in temporary crossings appeared in post-war highway construction manuals issued by the Bureau of Public Roads, 1961. For former German engineers, their legacy continued quietly. Several, among them Dr. Walter Wever Jr. and Erich Müller, became U.S. citizens and continued work at Belvoir through the 1960s. In 1965, the Fort Belvoir Museum unveiled a bronze plaque inscribed, "From Enemies in War to Architects of Peace." The dedication was attended by both American veterans and naturalized German engineers, a symbolic reconciliation forged through rivets and respect. Strategically, the bridging revolution proved critical throughout the Cold War. U.S. mobility doctrine, codified in Field Manual 5100, 1968, emphasized rapid deployment infrastructure, the same modular philosophy born from those 1947 Potomac trials. Even modern ribbon bridges and improved float bridges used in Iraq and Afghanistan trace their lineage directly to the Fort Belvoir innovations. Military historians now view the episode as a turning point in post-war science policy. As historian Colonel Edward Stack noted in 1989, "We learn that knowledge, even when captured, demands respect, and cooperation builds faster than conquest ever did." The legacy of America's bridge revolution endures not in monuments, but in motion, in every convoy that crosses a river, every relief mission that spans a flood, and every engineer who remembers that the strongest bridge ever built was made between former enemies. History often remembers bridges as lifeless steel and timber. Yet the story of America's post-war engineering triumph proves they can also connect ideologies, nations, and eras. The declassified U.S. Army educational pamphlet Bridges of Freedom, 1955, summarized it best. Our engineers did not rebuild what war destroyed. They reimagined how peace is built. From the ashes of Europe's devastation, American ingenuity, fortified by captured German precision and relentless discipline, created not just better bridges, but a blueprint for transformation. Major General Hugh J. Casey's final memorandum to the Corps of Engineers in 1953 captured the morale of this achievement. "We built more than bridges. We built understanding." The legacy of those engineers endures far beyond the rivers they spanned. Every time NATO convoys cross rapid deploy float bridges in exercises from Poland to Alaska, the lineage traces back to Fort Belvoir's 1947 test basin. Every humanitarian relief bridge that restores access after floods carries echoes of those early collaborations between former foes who turned rivalry into resolve. The story challenges our assumptions about victory. It reminds us that America's true strength was never just its arsenal, it was its capacity to learn, adapt, and rebuild with the very minds once sworn to oppose it. That capacity remains the heart of American resilience. As Cold War tensions eased, several of the original paperclip engineers faded into anonymity, but their work spoke louder than their names. When the Fort Belvoir Museum dedicated its commemorative hall in 1965, the inscription beneath their plaque read, "The span between war and peace is measured not in miles, but in understanding." The bridges they built, both physical and symbolic, still stand today. They remind historians and citizens alike that innovation thrives where curiosity defeats fear, and where yesterday's enemies become tomorrow's collaborators. Explore the archives. Learn the hidden stories behind the steel. Because every bridge you cross carries a lesson. Progress is strongest when built together.